This
Here,
conference will now be recorded.
or was it ended in the beginning itself or somewhere in the middle?
Ma'am, it was ended in the beginning itself.
Okay.
You just
Uh,
had started the ASIC flow.
okay.
Yeah, you
Mm,
just finished the verification and you wrote synthesis and the session got ended.
okay, okay. Just 1 minute. I'll just check and I'll let you know whether I need to give the demo or not. Once again, just 1 minute.
Oh.
Okay, yeah, I'll give the I'll start from where the meeting had got ended. So I'll start with ASIC flow. Okay, I'll start with ASIC flow. Okay. So the first step in ASIC flow is the design specification step. So based on a particular application, like based on a particular application for which we are developing the chip, the specifications will be decided, like what must be the speed, how many memory modules are required, how many sensors are required, what must be the power consumption. So these things will actually be um, decided by very experienced people in the field. They are called as architects. And next is the design code stage, where the Verilog code of the design will be written. So it will be written in behavioral modeling or else in data flow level modeling. Next, we need to validate the design which has been written during the design stage. So which is called as which will be done by verification team. Next comes the synthesis. So during synthesis, the RTL code, that is the behavioral or data flow level modeling code which we had written, it will be converted into gate level format, or it is also called as it will be like technology node specific, like 13 nanometer or sorry, 28 nanometer or 7 nanometer, like that. Next, we will be having design for testing. So design for testing, we will be adding additional logic into the design during the pre-silicon stage itself, in order to facilitate the detection of manufacturing defects in the chip. So we will be discussing about design for testing in our later slides. Next, we have the physical design team. So physical design team, they will be converting the gate level design into a layout form. and then we have the sign off. So sign off, they verify the static timing analysis STA, that is they verify whether there is any timing violations in various timing paths. Then they check for physical verification, that is they verify whether the layout of the circuit is done properly or not. And then they go for logical equivalence checks. So logical equivalence check, why it is done is, our design, it had started from our chip design, it had started from design code stage where we had the RTL code, that is in behavioral or behavioral model or data flow level modeling. Then we had the synthesis where we converted into gate level form, that is it is technology node specific like 28 nanometer technology. And then in between we will be adding those low power strategies, the cells, the special cells which are required for low power design like level shifters and phase shifters, retention registers, those things. And then we will be adding the DFT logic. So finally we are seeing whether the final netlist which we are having now, whether it is equivalent to the original RTL design. So in order to check that, we go for LEC, that is done by the sign off team. Next is tape out. Tape out is delivering the database to the manufacturing unit. And next we have the packaging and testing. So packaging is nothing but, so this is how a chip will look like. So this is a wafer, and this wafer will be divided into, like it will be made up of small areas called as dies. So covering this die with a protective layer is called as packaging. And testing is it is done after manufacturing. So we will check whether the chip is having whether the chip is passing or failing. So after manufacturing. So this is what is called as testing. So now we will discuss what is DFT. Sorry. So DFT, it is to insert test structures in the design. So this is done during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. So we will be adding some test structures into the design. So it will be done during the pre-silicon stage itself. So if suppose a particular defect occurs after manufacturing, or if a particular chip fails after manufacturing, so we will be able to tell what manufacturing defect has caused the chip to fail. So this is what is DFT. So DFT is to insert test structures in the design. This is done during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. Next we will see the role of DFT engineer. So DFT engineers, we will be adding some additional logic into the design to make sure that testing is done properly or not. So DFT engineers, they do not check the functionality of the chip. They rather check the quality of the chip. So for example, if we consider a half adder circuit, the functional verification engineer, what they will do is, they will apply the input sequence and they will get the output, and that output will be compared with the expected output. So this is what will be done by the functional verification engineer, that is they are checking the functionality. Whereas DFT engineers, we will be checking the quality of the chip, that is whether each and every net has any manufacturing defect or not. So we'll check like whether this net, whether it has got unintentionally tied to ground, or whether it has got unintentionally tied to VCC, VDD during manufacturing, or whether there is an unintentional short between these two nets. So likewise, in each and every net, we will check whether there is any manufacturing defect or not. So this is what is done by the DFT engineer. Now we will see what is testing. So testing, it is a process of determining whether a device, that is in this case chip, whether a chip is good or not. So testing basically includes test pattern generation, application and output evaluation. So during testing, what happens is, this test pattern will be actually generated by the DFT engineers during a process called as automatic test pattern generation. So these test patterns, it will be applied to the it will be actually given to a tester engineer. The tester engineer, they will be applying it onto the chip, and the output from the chip, it will actually be compared with the expected response. So in the test pattern itself, we will be having for this input sequence what must be the expected output. So the output from the chip, it will be compared with the expected output. So if a particular chip, if it fails after manufacturing, tester engineer, they cannot analyze it. So DFT engineers only can analyze what manufacturing defect has actually caused the chip to fail. So these are the possible outcomes of testing. So good IC passing the test, it is called as true pass. A defective IC passing a test is called as test escape, or it is also called as under testing. A good IC failing a test, it is called as yield loss, or it is called as over testing. And a defective IC failing a test is called as true reject. So goal of good testing, it will be to reduce the test escape and yield loss. So yield is nothing but out of a total number of chips manufactured, what percentage of chips are good? That is the number of good chips divided by total number of manufactured chips. So we'll see what are all the causes of manufacturing defects. So defects, they are basically caused by manufacturing defects. They are basically caused by process variation, like slight variation in transistor channel length, metal interconnect width or thickness. So these kind of issues, it will impact the logical and timing performance. And then some random imperfections, unintended shorts and opens. So those things are all random imperfections. We'll see the relation between defect, fault and error. A defect is, it is an unintended physical difference between hardware implementation and its intended design. So for example, if you consider an AND gate, this input of the AND gate, it is not intended to be tied to ground. But during manufacturing, unintentionally, as a manufacturing defect, unintentionally, this net, this input of this AND gate has got tied to ground. So this is what is called as a defect. Unintended physical difference between hardware implementation and intended design. Fault is, it is a logical abstraction, that is logical representation of physical defect. So this is a physical defect. So if it has to be represented in logically, then we can represent it as stuck at 0. So this is what is called as fault. Logical representation of physical defect is called as fault. And next is error. Error is, if we get a wrong output value, if we get a wrong value at the output, then that is called as a error. So for example, here we are giving a pattern of 1 1, but as this net, as it is tied to ground, the output value will be 0. So getting a wrong value at the output because of defect or fault is called as error. So we will see the flow of DFT. First we have the insertion phase, where we will be adding the extra logic. Then we have the generation phase, where we will be generating the test patterns, that is the input patterns and the expected sequence. And then we need to validate the patterns which was generated during this generation phase. So this generation phase, it is called as automatic test pattern generation. And validating the test patterns generated during ATPG time is called as simulation. So let's see the prerequisites of this course. So you first need to have digital design basics, that is combinational logic and sequential logic. Then basic electronics, that is CMOS circuits. Then any one of the HDL, like you can go with Verilog, a basic understanding of any one of the hardware description language, you can learn Verilog. And then understanding of VLSI design flow, which is the ASIC flow, which I had told previously. Next is any one of the scripting languages, that is Perl, Shell or Pickle. So I'll tell the course outline. So the first is scan insertion. Next we have compression. Next we have on-chip clock controller OCC, automatic test pattern generation ATPG, simulations, JTAG joint test access group, MBIST memory built-in self-test, and BScan, which is the boundary scan. So now I will discuss in short about these topics. It will be discussed in depth during the course. So scan insertion. Scan insertion, it is a process where all the normal flops in the design are converted into scan flops, and we are actually forming a shift register path or a Q to SI path, or it is also called as a scan chain. So all the normal flops, it is converted into scan flops, or it is like replaced with their scan equivalents, and we are forming a Q to SI path called as a scan chain. So the basic need of scan insertion is to gain controllability and observability of our design. So if we have controllability and observability of our design, we will be able to get a high test coverage for our circuit. So we'll see what is our controllability and observability, how we are gaining controllability and observability of the design when we go for scan insertion. So just consider an example that we are having a 10-bit counter. There is a counter initialization circuit and there is a counter observation circuit. So we'll just assume that the counter is failing. That is, after 999, instead of counting 1000, the counter again counts 999. We'll just assume that this is a manufacturing defect, or this is why the counter is failing. So after 999, on the 1000th pulse, the counter again counts 999 instead of 1000. So we will see how many clock pulses are required by functional verification team and DFT team to find out that the counter is failing. So functional verification team, as I told in the previous slide, they are going to check the functionality of the circuit. That is, our counter in our example, it is actually failing in the 1000th pulse. So that is at 1000th pulse, instead of counting 999, it is counting, instead of counting 1000, it is counting 999. So as functional verification team are checking the functionality, the counter has to count till 1000. So only then they will be able to tell, like at the 1000th pulse, the counter is still counting 999 and the counter is failing. So they require 1000 clock pulses. For this itself, they require 1000 clock pulses. They are checking the functionality of the counter. So they require 1000 clock pulses because the counter has to count till 1000. So only in the 1000th pulse, the counter is failing. So functional verification engineer, for this itself, they require 1000 pulses. And also there will be some pulses required for counter initialization as well as counter observation. So everything put together, functional verification team, they require more than 1000 pulses to tell that the counter is failing. The same thing, DFT engineer, we are not going to check the functionality, and as we are also gone for scan insertion, we can tell that the counter is failing in just 80 clock pulses or within 100 clock pulses. Okay, within 100 clock pulses, in less than 100 clock pulses itself, we will be able to tell how whether the counter is passing or failing. We'll be able to detect that the counter is failing. So how we are able to detect? So that we'll be able to understand when you have completed your scan insertion topic. So you need to know the operation of scan cell, and we need to know the scan chain operation. So only then you will be able to understand how we are able to tell in less than 100 clock cycles that the counter is failing. And apart from this, functional verification engineer, they can just tell that the counter is failing. But DFT engineer, we can tell what manufacturing defect has caused the counter to fail. So the MSB bit flop, its net might be stuck to 0, so that is why it is not becoming 1, or else the MSB bit net has a slow to rise fault, that is within the time period it has not got raised to 1, so that is why it is still counting 999. So like that, DFT engineers, we can tell what manufacturing defect has caused the counter to fail. Okay, so DFT engineers, in less number of clock cycles itself we can tell that the chip is failing, and we will also be able to tell what manufacturing defect has caused the chip to fail. So this is why we are going for scan insertion. Next is scan compression. So scan compression is a single scan channel is internally divided into multiple scan chain. So a single scan channel, it will be internally divided into multiple scan chain. So this is what is scan compression. The need of compression is to reduce test time and to reduce test data volume. So how it is done, we will be explaining it during the course. With the help of formulas, we will be explaining how compression reduces test time and test data volume. So this is what is compression. Next is automatic test pattern generation. So in automatic test pattern generation, we will be generating the test patterns. So what basically happens here? So we need to check what portion of the chip will get tested, and also to make the other portion of the chip to be testable, we go for ATPG. So in simpler words, if we have to tell, our tool will basically check if a particular defect occurs after manufacturing, will it get detected or not? Okay, our tool, it tries to check if a particular defect occurs after manufacturing, will it get detected or not? So there will be a question like, how does our tool know before manufacturing itself whether a particular manufacturing defect will get detected or not? So the answer to this question is, our tool performs a process called as fault simulation. So this is what is a fault simulation. So we will be giving the design to our ATPG tool. So ATPG tool will keep that design as such, that is a good design, good machine. Then the ATPG tool, inside its internal memory, automatically it will create a copy of the design. It will create a copy of this design, and in this design, so it will induce all possible manufacturing defects. So what are all the defects which can occur after manufacturing? All possible manufacturing defects, it will be inducing it in the circuit. So the logical representation of a defect is called as fault rate. So that is why it is mentioned here as fault list. So all possible defects, whatever can occur during manufacturing, all possible manufacturing defects, it will be inducing it in this circuit, in this design. And this is the bad machine or the faulty machine. Then the tool will write pattern for the good machine, and the output of the good machine is the expected output. The tool will apply pattern for the faulty machine, and the output of the faulty machine is the faulty output. Then it will check, then it will compare the good machine and the faulty machine output. So if good machine output and faulty machine output, if both are different, if good machine output and faulty machine output, if both are different. So for example, if good machine output is 1 and faulty machine output is 0. So if that particular defect occurs after manufacturing, then it will get detected. Okay, then it gets detected because expected value, good machine value and faulty machine value are different. So if good machine value and faulty machine value, if it is different, then those faults will be called as detected faults. If good machine output and faulty machine output, if they are same, that is if good machine output is also 1, faulty machine output is also 1, then if that particular fault, if that particular defect occurs after manufacturing, it is not getting detected because good value and faulty value both are same. So if good value and faulty value, if both are same, then the tool will consider those faults to be undetected faults, not detected faults. Okay, so good value and faulty value, if both are different, then those faults the tool will consider as detected faults. If good value and faulty value, if both are same, then the tool will consider the faults to be not detected faults. So if some faults are coming under not detected category, then we have to see why those faults are not getting detected, and we have to try our best to make sure that most of the faults will get detected. And during ATPG, our tool will be able to generate an optimized set of patterns. So why optimized set of patterns? Because whichever pattern detects all the faults, only those patterns our tool will be placing it in our final fault list. So for example, if you consider a simple AND gate, 111001, these three patterns are sufficient to detect all the faults in the AND gate. So in the final pattern list, the tool will just keep these three patterns alone. Okay, so instead of keeping all the possible combinations of patterns, only the patterns which will detect the faults, only those patterns is actually placed in the final pattern list. So that is why it is said that we will be able to generate optimized set of patterns during ATPG, and these patterns are only given to the tester to test the chip after manufacturing. Next is simulation. So to validate the patterns which were generated during ATPG, we go for simulation. So why we need to validate the patterns, it will be discussed as a part of our course. Next we have JTAG, Joint Test Access Group. So it is a IEEE standard, IEEE 1149.1 standard. So the main requirement of this JTAG is to minimize the number of ports from top level and to achieve boundary scan. So these are the two main needs of JTAG, to minimize the number of ports from top level and to achieve boundary scan. So we'll see like these two needs, we will see overview of these two things, we will see it in our upcoming slides. So I've just made a note of some signals. So these signals are required during MBIST. This is required during EDT. EDT is nothing but compression. And these signals are required for scan wrappers. So what is scan wrapper? It will be discussed during the course. So I've just listed a few important signals alone. Apart from these signals, there will be many more signals like this. So if all these signals, if they are to be controlled from the top level, then the number of ports from the top level, it will increase drastically. So that is why we are going for JTAG, to internally control these signals. So if we go for JTAG, internally these signals will be controlled internally through the JTAG logic, and from top level we'll just need 5 top level ports, that is 5 ports required for JTAG to control all these signals. So this is how JTAG TAP architecture will look like. So we have an instruction register and we have a group of data registers. This mux, it is used to select between the data register and the instruction register. And this mux, it is used to select one of the data registers from the various data registers present. So first, based on a particular application, like based on what we need to do currently, we will be loading the instruction into the instruction register. The output of the instruction register, it will actually be going as a select line for this mux. So based on that, one particular data register will get selected. So basically, instruction register, we will be loading value into the instruction register to select any one of the data register. So value will be loaded into the instruction register through this TDI. The value will be loaded into the instruction register. The output of the instruction register will be going to the mux. This mux, it is going as a select line to this mux. So it will actually select the one particular data register. For example, in this case, this data register has got selected. So core logic data register. So now during DR scan, what happens is required value will be loaded into the data register, and the output of the data register, it will be controlling the signals. So whatever should be the value of these signals. So whatever should be the value of these signals for that current mode. So for example, if you are doing in test mode, then int mode will be equal to 1, ext mode will be equal to 0, in L test enable will be 1, ext L test enable will be 0. So this value, it will actually be loaded into the data register, and that value only will be controlling these signals. The output of the data register only will be controlling these signals. So this is how we are internally controlling the signals instead of controlling it from the top level. So we will discuss in depth about what is a JTAG tap and what is a JTAG FSM. So you'll be having a JTAG FSM, JTAG controller. So what are all the states which is present in the JTAG controller? What is the actual structure of instruction and data register, and more in depth. So all these things will be discussed in depth during the course. I've just given an overview of it. Next is boundary scan. So why we need to go for boundary scan? So say for example, there are 3 chips. So chip 1, chip 2, chip 3 are there. These 3 chips, after manufacturing, they have got tested on the tester and they have passed their test. But once they are placed on the PCB board, the PCB board is failing. Okay, chip 1, chip 2, chip 3, they have passed their test individually. But when they are placed on the board is failing. So the reason can be is there can be manufacturing defects in the interconnection between the 2 chips. Okay, because there is no manufacturing defect in chip 1, chip 2, and chip 3, because chip 1, chip 2, and chip 3, they have individually passed their tests. But still the board is failing. So the reason can be there is a manufacturing defect in the interconnection between the 2 chips. So in order to test the interconnection between the 2 chips only, we go for boundary scan. So the chip what we have shown here, it will actually look like this. So we'll be having pads, and then like we'll be having here, you'll be having the core logic. So from external world through the pad, the data will be given to the core logic, and from the core logic through the pad, the data will be given to the outside world. Core logic is nothing but the logic of the chip, that is the combo logic and flops. So we'll discuss it in depth, like how boundary scan is done, what additional logic has to be inserted to achieve boundary scan, and those things we will be discussing it in the course in depth. So next we'll see the IEEE 1687 standard, which is the IJTAG standard. It is the internal JTAG. So previously we had seen like in JTAG through the TDI. So TDI, it was directly like the tap was actually through the TDI, it was controlling the TDRs directly. The value from the TDI, it was going and it was written into the TDR. That is the data register. But here in IJTAG, we will be having another additional component called as the SIB. So the value from the TDI, it will be written to the TDR through the SIB. So through the SIB is called as segment insertion bit. It acts as a chip. It acts as a switch. So the data from TDI, it will be written into the TDR through the SIB. So for example, so this SIB, it can either be programmed to 0 or 1. So if the SIB is programmed to 1, if a SIB is programmed with 1, then that means it is open. And if a SIB is open, then it will allow the data to be written into the TDR. So we'll assume that the SIB 1 is open now, that is, it is programmed with 1. Then the data from TDI, as the SIB is opened, it will be written into the TDR and it will be coming like this. If the SIB was closed, that is, if the SIB is programmed with 0, then the data from the TDI, it will not be written into the TDR, it will directly go like this. So this is what is SIB. So this additional architecture, the additional logic which is there in this IEEE 1687 standard, this is called as a SIB. Okay. So now we will see a 2-instrument network with SIB. So basically, if a SIB is open, then that means it is programmed with 1, and if a SIB is closed, it is programmed with 0. So we'll just see the data flow. For example, we'll consider that this is SIB 1 and SIB 2. We will assume that SIB 1 is opened, that is, it is programmed with 1. Then it will allow the data to be written into this TDR like this, and SIP2 is closed, so the data will be like this, going like this. This is the flow of data path. And if SIP1 is closed, that is programmed with 0, and SIP2 is opened if it is programmed with 1, then what will happen is data from TDI, it will be coming like this. So as this is closed, through this SIP, it will be going here. This SIP is opened, so the data will be written into the TDR and it will be coming. So if suppose if both the SIPs are open, so if both the SIPs are open, then the data from TDI, as this SIP is open, it will be written into the TDR, and as this SIP is also open, it will be written into this TDR, and it will be going like this. The output of this TDR only will be going to the logic, okay, in order to control the logic, in order to control the signals. So this is what is IJTAG standard. So additional component is this SIP. So the SIP, if the SIP is there, then that is 1687 standard, IEEE 1687 standard. So this is how IJTAG will basically look like. So during IR scan, by loading appropriate value into the instruction register, we can select the IJTAG network. And when if IJTAG network is selected, then through this TDI, we can program the SIP and the TDRs. Okay. So this structure is similar to what we had seen in the previous slide. Now next we will see about memory built-in self-test MBIST. So here if you see, there are many memories in this design, which are actually like instantiated in two different cores within the chip. So this is one single chip. So one set of memory is actually present in this core, it is given by dotted line, and the other set of memory, it is actually present in the other core. So memories are nothing but this orange color, yellow orange, what we see here, these are the memories. So each memory, it should have an interface. So each memory should have an interface. So what I am pointing out here, that is called as an interface. So each memory, it should have an interface. So why we require an interface, I'll tell during the next slide. So these interfaces, they are actually controlled by this TMB. TMB stands for Tessent Memory BIST Controller. So these interfaces, they are controlled by TMB, that is a Tessent Memory BIST Controller. And this Memory BIST Controller, they are in turn controlled by BAP. BAP is nothing but BIST access port. So the TDRs will actually be present inside this BAP. And then this BAP is in turn controlled by SIP, and the SIP is in turn controlled by the TAP. So a TAP is nothing but from this TAP only you will be having this TDI. So through the TDI, the data will be written, the SIP will be programmed to either 0 or 1, and also the necessary value will be written into the TDR. So this TDR will actually be present inside this BAP. Okay, so from the BAP, it will be going to the controller to control various signals, and the controller will actually be controlling the memory interfaces. So this is how our memory circuit will look like. So this is our memory, and this is what is called as the memory interface, and this is the BIST circuitry. So the memory interface, it will basically consist of various muxes. It will be basically consisting of muxes. So these muxes, they are used to select between a test input and a functional input, test input or a functional input based on this BIST on signal. So this BIST on signal will be coming from the FSM which is present in the BIST controller. Okay, so the BIST on signal will be coming from the FSM which is present in the BIST controller. If this BIST on signal is 1, then the memory is in test mode and test input will be selected. If BIST on signal is 0, then memory is in functional mode and functional data will be selected. So if BIST on signal is 1, if the memory is in memory mode, then what happens is the FSM and the signal generator together, they will be writing appropriate data into the memory, and also the same data they will be writing it inside this comparator. Now the output of the memory, it will again be given to the comparator. It will be given to the comparator, and both these values will be compared. So if the value which was already there in the comparator, that is the expected value, if the expected value, if it is same as the value which is coming from the memory output, then there is no fault in the memory, then there is no defect in the memory. If both are different, then there is some defect in the memory. So this is the Tessent memory BIST operation protocol. So in order to, so here if you see, we'll be having this BIST setup and BIST PG enable signal, which will be given to the memory BIST controller. So these signals will actually be controlled by the BAP. Okay, so the necessary values will be written into this BAP through the TDI, and when the switch, when the SIB is programmed to 1. Okay, so these are actually controlled by the BAP. So this is what is the Tessent memory BIST operation protocol. So the BIST setup signal has to be controlled to 1 0, and BIST PG enable signal has to be made 1. So this will be controlled by the BAP. And then this go bit and done bit, these are actually basically the output bits. So in order to start the memory BIST operation, we need to make this BIST setup signal to 1 0 and BIST PG enable signal to 1 in order to start the memory BIST operation. So the go and done bits, they are like output bits. So the go bit, it will be first 1 and it will completely remain 1 if there are no faults in the memory or if there are no defects in the memory. If suppose some fault has got detected in the memory, then the go bit will go low. And done bit it will be low and it will go high only when the test has got completed. So this is the Tessent memory BIST operation protocol. So these are the theoretical topics. So I have discussed an overview, given an overview of these topics which will be discussed during the course in depth. So I'll see what are all the labs which are available. So we have IJTAG, MBIST, scan insertion. There are two types. One is like top-down approach and the other one is bottom-up or hierarchical approach. So we are having test cases for both these approaches. Then EDT OCC insertion. EDT is compression and OCC will be discussed during the course on chip clock controller. So the need of OCC will be discussed during the course. Then automatic test pattern generation. And finally, simulations. So during MBIST also will be generating the patterns and during ATPG also will be generating the patterns. Both the patterns we will be doing the simulations. And these are all the tools which is used for DFT in the industry. So in our institute, we will be using Mentor Graphics tool. For MBIST insertion, we will be using Tessent MBIST. For scan insertion, we will be using Tessent DFT Advisor, or it is also called as Tessent Scan. For compression, we will be using Tessent Test Compress. ATPG will be using Tessent Test Compress itself, and simulations will be using Questas. And for synthesis alone, we will be going for design compiler, which is the synopsis tool. So synthesis is actually not a part of DFT. We need to do synthesis in one stage. Okay, so for that we will be using design compiler, which is the synopsis tool. So that is it for my demo. So those things will be discussed during the course. So advantage of IJTAG over JTAG, those things will be discussed as a part of the course.
Hello, hi.
Yes, tell me.
Yeah, I wanted to ask, how are the weekend courses kind of split up, right? Can we have more details on the weekend courses? How are the
Okay.
different sessions split up? Yeah.
Okay, just 1 minute. I will contact someone from management side. They will be addressing this doubt. So just 1 minute. Okay, so sir is not picking up the call. So I'll give you the contacts. I think you can, I'll share the number in the chat box. So you can contact them after this demo session and you can get it clarified.
Yeah. So just asking one thing, right? Just the basic, right? So you said that there will be lab sessions, right? So,
Yeah.
like in general, what is the, what is the ratio between theoretical and practical courses for weekend classes?
So say for example, we have done scan insertion theory if you have completed during the theory session. So the same
Mhm.
thing will be demonstrated practically during the practical sessions. So
But
test
how
cases
many
will
hours
be
is the
given.
practical sessions? How many hours is a practical session? Any idea?
So it will be during the weekends and it will be around 2.5 hours to 3 hours on Saturday, Sunday,
And the
on
theoretical,
Saturday
the
as well as on
overall,
Sunday.
so on Saturday, what is the total number of hours that we'll be having?
Saturday, I think like for theory sessions, we'll be having around 3 hours, and I think it will be there in the morning. And during the afternoon, you'll be having like lab sessions, so which will be for around 2.5 hours or 3 hours.
So how about the
So total will be,
online people? So how about the online guys? How for them is the same? Whoever attends this course
uh,
online?
yes, it is the same.
So altogether, I would say 6 hours, right? 5 to 6 hours on Saturday and Sunday.
Yes, on Saturday
I
6 hours,
see.
Sunday 6 hours. Yes.
Okay. And is this will this be customized based on the needs of the people, or will it be more like, how to say, it's a fixed number of hours?
Uh, I'm not very sure. I'll give you the contact numbers. You can
Okay,
contact
please.
them after the demo session and you can just check it out.
Okay,
Just one
thank you.
minute. For others also, if you're having some doubts related to like when the course is starting or like how the course will go, I'll give you the numbers. So I can contact sirs during after this demo session. So just a minute, I'll share with you the numbers. So I have shared their numbers. So any one of them you can contact, and after this demo session, you can contact anyone, and you can get clarification regarding the sessions, and also like the course start date and end date, and also regarding placements. So you can like contact them, and you can get the informations. Will we be
Okay, sounds
getting
good. Thank you.
PPTs and yes, thank you. Yes, Nagaraj, you'll be like PPTs will be available in the InSkill portal, and recordings of the sessions will also be available in the InSkill portal itself. Yes, for all the sessions it will be available.
Ma'am, will they be all the time, or are there any restricted timings where we can access them?
No, anytime you can access 24/7.
Anytime access it.
Yes.
And when is the course starting? Next week, right? Next weekend, right?
Yeah, that's what I'm not sure. You can check with any one of these three sirs, like when the course is starting and what will be the duration of course, and also regarding the sessions. They are from management, so they will be informing it to you. You can contact any one of them, and you'll get clarification.
Okay, sounds good. Thank you.
Okay, so do you have any other doubts? Okay, so thank you all. I'm winding up today's demo.
Ma'am, will there be any other session after this, or this is the end of the today's session?
Yeah, I'm not sure. You can check with. You can either message in your personalized group, or you can check
Okay,
with any one of these three servers. I think you can
sure.
message in your personalized group, so everybody will be there in that group, so they will respond to you.
Okay, thank you.
Okay. Thank you all. I'm winding up today's session.
Thank you.